When the USS Nimitz first cut through the waters in 1975, it didn't just represent another addition to the United States Navy fleet. It marked the dawn of a new era in naval warfare. This floating city, stretching 333 meters and displacing more than 100,000 tons, would fundamentally reshape how nations project power across the world's oceans. The aircraft carrier has long been the crown jewel of naval forces, but the Nimitz class took this concept to new heights. These nuclear-powered giants didn't merely expand existing capabilities, they created entirely new strategic possibilities that continue to be relevant nearly 5 decades later. Today, we'll examine how these remarkable vessels transformed naval air power, from their design features to their lasting impact on power projection strategy. To understand the true significance of the Nimitz class, we must first establish what distinguishes a supercarrier from its smaller cousins. The term supercarrier emerged during the Cold War to describe aircraft carriers of exceptional size, capability, and operational reach. But pinpointing the first true supercarrier requires careful analysis of both capability and intent. The debate over the first true supercarrier often centers on the Forrestal class, commissioned in the 1950s. These carriers represented a leap in naval aviation capability, featuring angled flight decks, steam catapults, and the ability to operate the new generation of jet aircraft that were transforming air warfare. With a displacement of approximately 60,000 tons and a length of over 300 meters, the Forrestal class established the template for what we now recognize as the modern supercarrier. But the Forrestal class, revolutionary as it was, still relied on conventional propulsion. This meant they were tethered to supply lines, dependent on regular refueling, and limited in their operational endurance. They were powerful, yes, but they weren't yet the self-sustaining fortresses that would later define the US Navy. The USS Enterprise, commissioned in 1961, changed everything. As the world's first nuclear-powered aircraft carrier, she was a bold experiment in extending the reach and the independence of the US Navy. The logic for nuclear propulsion was clear. The Navy wanted a carrier that could remain at sea for months without the constant burden of refueling, which had always been a major limitation of large capital ships. In the Cold War, where US carriers were expected to operate far from home ports and potentially deep in Soviet-controlled waters, freedom from oil tankers meant both operational flexibility and strategic survivability. Enterprise was powered by 8 Westinghouse A2W nuclear reactors, 2 per propeller shaft, a design that reflected the Navy's cautious approach to its first nuclear carrier. Each reactor was smaller than the ones later installed on the Nimitz class, and the 8-reactor layout gave the ship enormous power for propulsion and shipboard systems, but at a high cost. This arrangement allowed the 93,000-ton carrier to sail indefinitely, with endurance limited only by food, aviation fuel, and crew fatigue. Unlike conventional carriers, which needed to refuel every several thousand nautical miles, the Enterprise could conduct sustained operations across the globe without a single stop for bunker fuel. The nuclear propulsion system also offered unique tactical and strategic advantages. During the tense years of the early Cold War and the Cuban Missile Crisis, the ability to sprint across oceans at full speed without refueling meant that Enterprise could respond to crises faster than any previous carrier. She could operate far from friendly bases or supply lines, making her far less vulnerable to the disruption of logistics. a critical consideration in any potential conflict with the Soviet Union. Yet, the ship's pioneering design also revealed the growing pains of first-generation nuclear carrier technology. The 8-reactor configuration, while conceptually providing redundancy, made the engineering plant extraordinarily complex and maintenance-intensive. Reactor operations required a larger, highly trained engineering crew, and the cost of maintaining and eventually refueling so many reactors was immense. Enterprise fulfilled her mission as a proof of concept, showing that a nuclear-powered carrier could fundamentally alter the strategic calculus of naval operations. But her design would never be repeated. It was the lessons learned from Enterprise, her success in endurance and speed, and the complication of her maintenance-heavy reactor layout that directly informed the streamlined 2-reactor design of the Nimitz class. The new carriers achieved the same operational freedom with far greater efficiency, representing the maturity of the nuclear supercarrier concept that Enterprise had first brought to life. The heart of the Nimitz-class revolution lies in its refined nuclear propulsion system. 2 A4W pressurized water reactors, each linked to a pair of steam turbines that drive 4 propeller shafts. Unlike Enterprise, which uses 8 smaller reactors, the Nimitz class concentrates its power into 2 large reactor plants that can deliver roughly 194 megawatts of shaft power combined, or about 260,000 shaft horsepower. Each A4W reactor heats pressurized water to produce steam, which then drives the ship's main propulsion turbines. These turbines are connected to reduction gears that slow the extremely fast rotation of the turbines, thousands of revolutions per minute, down to the much lower speed required by the 6.4-meter 5-bladed propellers. 2 shafts are driven by each reactor's turbine assembly, allowing the carrier to maintain propulsion even if one reactor is taken offline for maintenance or damage control. This arrangement provides both redundancy and efficiency without the complexity of an 8-reactor setup. The steam produced by the reactors does more than spin the propellers. Branch steam lines feed the ship's electrical generators, which supply power for radar, sensors, catapults, elevators, lighting, and life support systems. Additional steam drives the catapults that launch aircraft, while auxiliary steam turbines power pumps and compressors throughout the ship. By integrating propulsion and power generation into a single steam cycle, the Nimitz class eliminates the need for separate fuel-hungry boilers and diesels for most ship functions. Because the reactors can operate for roughly 20 to 25 years without refueling, the propulsion system allows the carrier to sustain high-speed operations across entire oceans without any logistical pause for refueling. If we ignore the constraints faced by the escorts, then the only true limits to the carrier's endurance are aviation fuel, food, and spare parts. In combat, this configuration allows the carrier to sprint to a theater, remain on station for months, and conduct sustained flight operations without the constraints that dictated the movements of conventional carriers. This integration of reactors, steam turbines, reduction gears, and 4-shaft propulsion creates a system that is both more maintainable than Enterprise and capable of delivering consistent, high-speed power. It is this overall engineering, not just the nuclear cores themselves, that enables the Nimitz class to serve as a persistent, mobile airbase anywhere in the world. This operational freedom transforms the carrier from a powerful but constrained weapons platform into an instrument of sustained power projection. The nuclear revolution extends far beyond the carrier itself. It's fundamentally altered the operational dynamics of the entire carrier strike group. While the escorts, destroyers, cruisers, and supply ships remain conventionally powered, the carrier's nuclear endurance becomes the defining factor for the group's operational tempo and deployment's duration. This means the strike group's endurance is limited not by the carrier's power plants, but by the fuel capacity of its escorts and the logistical supports required to keep them operational. In practice, this tends to extend deployment's durations, enables sustained presence, and provides commanders with flexibility. Escorts, like cruisers and destroyers, are naturally far more fungible and easier to find than the aircraft carrier. The staying power has profound strategic implications. A nuclear carrier strike group can maintain continuous presence in contested waters, respond to multiple crises within a single deployment, and sustain combat operations far longer than any conventionally powered naval force. The psychological impact on potential adversaries cannot be overstated. The knowledge that a nuclear carrier can maintain its position indefinitely changes the strategic calculus of any potential conflict. Now let's examine the general design of the platform itself. With a full load displacement of approximately 100,000 tons, the Nimitz ranks among the largest warships ever constructed. Their sheer scale is difficult to comprehend. 333 meters in length, with a flight deck beam of over 76 meters. These aren't just ships, they are floating cities dedicated to naval air power. The hull design reflects decades of experience in carrier operations. Built for endurance and survivability, the Nimitz class features a robust hull form designed to maintain stability during flight operations, even in heavy seas. This isn't merely about crew comfort, it's about maintaining operational capability when conditions would ground land-based aircraft. The flight deck represents the culmination of carrier aviation engineering. 4 steam catapults, strategically positioned on an angled flight deck configuration, enable the rapid launch of aircraft in close succession. Each catapult can accelerate a fully loaded fighter aircraft from 0 to over 250 kilometers per hour in under 3 seconds, delivering the kinetic energy required to launch even the heaviest aircraft from a moving platform. The angled deck technically allows aircraft to land while others launch from the bow, but the US Navy conducts flight operations in cycles rather than true simultaneous launch and recovery. This approach maximizes safety and efficiency during sustained operations. Beneath each catapult lies the catapult control station, known as the bubble. Manned by a catapult officer, this pressurized booth coordinates steam buildup, launch timing, and safety interlocks. Through reinforced glass, the officer monitors deck crew signals and aircraft position, ensuring precise, synchronized launches during high-tempo flight operations. 4 aircraft elevators, each capable of handling over 36,000 kilograms, move aircraft between the hangar deck and flight deck with mechanical precision. 3 of these elevators are located along the starboard side of the ship, forward, amidships, and aft, while the 4th is positioned on the port side near the stern. The starboard elevators handle the majority of aircraft movements during flight operations, as their placement aligns with the main taxi routes and launch areas on the angled flight deck. This arrangement helps optimize aircraft flow, minimize deck congestion, and maintain operational tempo during intensive flight operations. Having 4 elevators produces the benefits of redundancy, which ensures that even with one elevator out of service, for example, due to damage, flight operations can continue uninterrupted. The arrestor gear system, 4 precisely calibrated cables stretched across the landing area, represents one of the most demanding engineering challenges in naval aviation. These allow the safe landing of fixed-wing aircraft. These cables must safely decelerate aircraft weighing tens of thousands of kilograms traveling at over 200 kilometers per hour, bring them to a complete stop in roughly 100 meters. The system must perform this function thousands of times during a deployment, with absolute reliability, because failure means aircraft and potentially the crew lost at sea. Another critical, yet often overlooked component of aircraft recovery is the optical landing system, nicknamed the Nimitz. This system provides real-time visual guidance to incoming pilots during final approach. Using a series of lights and lenses mounted beside the landing area, the optical landing system shows pilots whether they are on a safe approach angle or not. If too high or too low, the Nimitz will shift position. In combat or rough seas, this compact system ensures safe recoveries under extreme conditions. The US Navy carriers generally launch and recover aircraft in cycles, not simultaneously. A typical flight cycle lasts about 90 minutes. During the launch phase, aircraft are taxied from the hangar and parked at designated spots on the flight deck, where they are fueled, armed, and checked by deck crews. The first aircraft are positioned on the bow and waist catapults, and launches occur in quick succession, roughly 1 aircraft every 30 to 45 seconds. During surge operations, aircraft can be launched more rapidly for short periods. Once the strike package is airborne, the deck is reorganized for recovery. Arresting cables are rigged, and recovery begins with airborne early warning systems, followed by electronic warfare aircraft, and finally by fighters. After each trap, aircraft are quickly cleared from the landing area and moved forward to the bow to be refueled, rearmed, and prepared for the next cycle. This rhythm allows the carrier to maintain a high sortie rate without the hazards of simultaneous launch and recovery. The typical air wing of a Nimitz-class carrier was historically around 80 aircraft, although modern deployments are generally closer to 60. But this number understates the versatility in its balance and composition. The composition of the air wing reflects the multi-mission requirements of modern naval aviation. FA-18E Super Hornets provide strike capability and air superiority. The E-2D Hawkeyes extend radar coverage hundreds of kilometers beyond the horizon. The EA-18G Growlers deliver electronic warfare capabilities that can blind enemy sensors and communications. The MH-60 Seahawks provide anti-submarine warfare, search and rescue, and logistical support. This air wing can simultaneously conduct air superiority missions, combat air patrol to defend the carrier force, precision strikes against land targets, maritime surveillance, electronic warfare, and anti-submarine operations. The carrier becomes not just a platform for aircraft, but a multi-dimensional warfare system capable of dominating air, surface, and subsurface domains simultaneously. The sensor and communication suite of a Nimitz-class carrier rivals that of many large ground-based installations. The AN/SPS-48E three-dimensional air search radar provides precise range, bearing, and altitude data on aerial contact at extreme ranges. The AN/SPS-49 two-dimensional radar offers broad area surveillance, creating a comprehensive air picture extending a long range from the ship. Air traffic control relies on the AN/SPN-43 radar system, managing the complex choreography of aircraft launches and recoveries that occur every few minutes during intensive operations. This isn't civilian air traffic control, it's precision timing under combat conditions, where a mistake can result in catastrophic aircraft collisions or failed recoveries. Satellite communications provides secure global connectivity, enabling the carrier to receive targeting data, intelligence updates, and strategic guidance from anywhere in the world. Multiple radio systems across a range of frequencies, including high frequency, very high frequency, and ultra high frequency, ensure redundant communications across all frequencies and ranges. Most critically, Link 11 and Link 16 tactical data links create a real-time information network connecting the carrier with its escorts, supporting aircraft, and shore-based command centers within a reasonable distance. This communications architecture transforms the carrier from an isolated platform into a node in a global information network. Intelligence gathered by the carrier's aircraft can be instantly shared with other units. Targeting data from satellite surveillance can guide the carrier strikes. Strategic guidance from Washington can reach the carrier commander within minutes of transmission. The Nimitz class also feature extensive onboard maintenance facilities that rival many shore-based installations. The hangar contains fully equipped machine shops capable of fabricating parts using milling machines and welding equipment. Specialized electronic repair workshops handle avionics, radar, and communication system maintenance, allowing rapid restoration of vital sensors and control systems. Dedicated aircraft maintenance space provides space and tooling for airframe repairs, engine overhauls, and weapon system servicing, enabling the air wing to remain mission-ready during extended deployment. To support these capabilities, the carrier carries a vast inventory of spare parts, consumables, and raw materials stored throughout the ship in secured magazines and storage areas. Replenishment comes primarily from underway replenishment ships, oilers, supply ships, and ammunition ships that deliver fuel, munitions, and critical supplies via connected replenishment or helicopter vertical replenishment. This supply chain ensures the carrier and its air wing can operate independently for extended periods without port visits. Additionally, the carrier's well-established logistical network coordinates with shore bases worldwide to pre-position parts and conduct maintenance during scheduled visits, minimizing downtime. Survivability on the Nimitz class is built around multiple layers of protection and resilience. While not heavily armored like the battleships of the past, the carrier incorporates armor plating around critical areas, such as flight deck edge, hangar sides, and machinery spaces to reduce vulnerability to explosive fragments and shock damage. The hull and internal structures utilize high-strength steel and compartmentalization to localize damage. A robust damage control system integrates sensors, firefighting stations, and damage control parties trained to respond rapidly to fire, flooding, or structural damage. The ship is divided into multiple independent fire zones and floodable compartments, each equipped with remotely controlled watertight doors and valves. The segmentation allows crews to isolate damaged sections, preventing fire and flooding from spreading throughout the ship. Redundant systems for power, communications, and steering ensure the carrier can maintain essential functions even if primary systems are compromised. Damage control teams conduct continuous drills and maintain readiness to tackle chemical, biological, radiological, or nuclear threats, as well as conventional battle damage. The design reflects hard-earned lessons from World War II, when carriers suffered severe damage but often survived due to quick firefighting and compartmentalization. The Nimitz class's layered defense and damage control philosophy allow it to absorb damage, maintain flight operations, and remain a resilient centerpiece of naval power projection. These design features combine to create more than just a ship. They create a complete weapon systems optimized for sustained high-intensity operations in contested environments, and to survive in such an environment. The Nimitz class doesn't just carry aircraft. It sustains, launches, recovers, and maintains them under conditions that would challenge any land-based installation. A fully deployed Nimitz class carries around 5,200 to 5,500 personnel, roughly 3,200 in the ship's company, about 2,000 in the air wing, and up to 500 in embarked staff or marines. Accommodations are arranged to sustain the crew through months-long deployments. Most sailors live in multi-tiered bunk rooms with 6 racks per compartment. Each bunk includes a personal reading light, ventilation, and a small locker for personal items. Officers are housed in 2 or 4-person cabins that provide more space and privacy. Feeding such a population requires significant onboard capacity. The ship has 5 main galleys, the naval term for kitchens, which operate around the clock. They can collectively prepare over 17,000 meals per day. Adjacent mess decks serve these meals in continuous rotations, organized by watch schedules to ensure the entire crew can be fed efficiently. Life support systems enable the carrier to function as a self-contained city. Fresh water is produced on board using large distillation and desalination plants, generating over 1,500,000 liters of fresh water per day for drinking, cooking, and sanitation. Food for months of operations is stored in deep refrigerated and dry storage compartments, allowing the carrier to remain at sea for roughly 90 days without resupply. Waste is processed by onboard sewage treatment plants and trash handling systems that compact, incinerate, or store refuse for disposal ashore. In addition to these essentials, the carrier houses a medical and dental clinic, gymnasiums, a chapel, a post office, and limited recreation spaces such as a library and a small movie area. Together, these facilities allow the ship to sustain its large crew and maintain morale during extended deployments far from shore, reinforcing the carrier's reputation as a self-sufficient city. The influence of the Nimitz class extends far beyond American naval operations. These carriers established the benchmark against which all future supercarriers would be measured. The Gerald R. Ford class, now entering service, represents an evolution of the Nimitz class concept rather than a revolutionary departure. Electromagnetic catapults replace steam. More advanced radar systems provide greater sensitivity, and improved A1B reactors offer greater power. But the fundamental concept of a nuclear supercarrier remains unchanged. The Nimitz class also influenced carrier development worldwide. While no other navy has matched the scale and capability of these ships, The operational concepts pioneered by the Nimitz class, nuclear propulsion, multi-mission air wings, and sustained presence operations have shaped carrier developments from the Queen Elizabeth class to the supercarriers that China is building. Perhaps most significantly, the Nimitz class established the modern carrier strike group doctrine that remains the foundation of American naval strategy. In this framework, the carrier serves as the primary offensive platform, projecting air power far beyond the fleet, while escort ships, guided missile cruisers, air defense destroyers, and attack submarines are fundamentally designed and armed to provide layered protection for the aircraft carrier. These escorts shield the carrier from aerial, surface, and subsurface threats, allowing it to operate with relative freedom. Although this doctrine has been exercised and proven effective in regional conflicts such as the Persian Gulf and operations against ISIS, these engagements have primarily involved asymmetric warfare or regional adversaries. The Nimitz-class carrier group has always operated in the context of overwhelming American naval dominance. The true test of a carrier strike group's capabilities against a peer naval power with advanced anti-access and area denial capabilities remains a major challenge yet to be faced, at least to any substantial degree. Nevertheless, on a technical level, the transformative impact of the Nimitz class cannot be overstated. These ships didn't just represent an improvement in carrier design. They fundamentally altered the nature of power projection for the US Navy. Nuclear propulsion freed carriers from the constraints of fuel and logistics that had limited naval operations since the age of steam. The massive scale and sophisticated systems of the Nimitz class enabled sustained multi-mission operations that were previously impossible. For over 4 decades, the Nimitz class has served as the backbone of American naval power projection. These ships have responded to crisis, deterred and in some cases initiated conflict, and projected American influence across every ocean. They have adapted to changing threats, incorporated new technologies, and maintained their relevance in an era of rapid military innovation. As we look toward the future of naval warfare, the fundamental concepts pioneered by the Nimitz class, nuclear propulsion, massive scale, multi-mission capability, and sustained endurance remain as relevant as ever. The threats may evolve, the technologies may advance, but the requirements for sustained naval power projection persist. The Nimitz-class supercarrier stands as perhaps the most successful naval system of the post-war era. In an age of rapid change and emerging threats, the Nimitz-class remains what it has always been, the ultimate expression of naval air power. They show why the supercarrier is the ultimate capital ship of the modern era. Thanks for watching. See you next time.